Artificial groundwater recharge. Artificial groundwater recharge is a process by which the groundwater reservoir is augmented at a rate exceeding under natural conditions for replenishment. Any man made scheme or facility that replenishes depleted aquifers may be considered as an artificial recharge system structure. It may be planned, as in the case of the pit or well drilled for the purpose of storing water into an aquifer, or may be planned or unplanned or incidental to human activity, as in the case of surface water irrigation. Most artificial recharge projects are planned for the specific purpose for saving water or storing fresh water for its subsequent use for domestic or irrigation purposes. Need groundwater recharge is essential due to the following. The groundwater is to be used as a sustainable resource as surface water is inadequate to meet our requirement. Infiltration of rainwater into the subsoil has decreased drastically, and the charging of groundwater has diminished due to the rapid urbanization. Overexploitation of the groundwater resource has resulted in decline in water levels in most parts of the country. The availability of the groundwater needs to be enhanced by conservation and storage of excess surface water for future requirements. The sewage enters into the coastal areas need to be checked due to the overpumping of groundwater. The groundwater quality, brackish saline, needs to be improved. Brackish or saline. The vegetative cover needs to be increased to improve the ecology of the area, and the water levels in wells need to be raised to reduce power consumption and eventually increases the agricultural production. Benefits: the cost of recharge to subsurface reservoir is lower than the surface reservoirs. An ideal solution of water problem in areas having inadequate surface water sources like canals and lakes and village ponds raises groundwater levels. Groundwater is not directly exposed to evaporation and pollution. It mitigates the effects of the drought and achieves the drought proofing, reduces runoff which chokes the stormwater drains and also reduces flooding of roads and parks, improves groundwater quality, reduces soil erosion, and saves energy in the lifting groundwater. 1 meter of rise in water level saves about 0.40 kilowatt hour of electricity. The ideal condition for artificial recharge. The basic requirement for artificial recharge to groundwater are the availability of the adequate quantity of water from rainfall or surface water canals. An adequate space for storage is not available on ground. Availability of the suitable sites for construction of recharge structure at low cost. Water table is deep enough. An adequate subsurface storage space is available. Decline in water levels on the regular basis in natural recharge has been reduced substantially because of urbanization and concretization of the land surfaces. In areas where substantial amount of aquifers is dried up, in areas where availability of the surface water is inadequate in lean periods, and in areas where due to urbanization infiltration of rainwater into subsoil has decreased drastically and recharge to groundwater is diminished. Then we have the design considerations. Three most important components which need to be evaluated for the designing the artificial recharge structures are the hydrogeology of the area, including nature and extent of aquifers, soil cover, topography, depth to water levels, and chemical quality of the groundwater. Area contributing to runoff, that is how much area and land use pattern, whether industrial, residential, or general built up pattern of the area. And the hydrometeorological characteristics through rainfall duration, general pattern, and intensity of the rainfall. How much water can be harvested? The runoff generated from the rainfall in an area is dependent upon catchment's area, collection efficiency of that area, and amount of rainfall falling on that area. Runoff amount, the catchment area, and the runoff coefficient into rainfall depth. Runoff coefficient is a factor which indicates that all the rainfall falling on the catchments cannot be collected. Some rainfall is lost from the catchments by evaporation and retention on the surface itself. The percentage of water which flows out from an area is known as the runoff coefficient. It plays an important role in assessing the runoff availability and depends upon the catchment's characteristics. General values of runoff coefficients which may be utilized for assessing the runoff availability A wide spectrum of methods and techniques are used to recharge groundwater reservoir based on the hydrogeological conditions of an area. Different methods are used for the efficient results. The artificial recharge techniques can be broadly categorized as follows. Direct surface techniques are the basins or percolation tanks, ditch and furrow system, check dams, nala bunds. Gabion structures, direct subsurface techniques are the recharge pits, recharge trenches, and the recharge shafts. Injection wells or recharge wells, dug well recharge. Combination of surface and subsurface techniques are the basin or percolation ponds with the pits, shafts or wells, recharge pits with tube wells, recharge shaft trenches with tube wells. Artificial recharge methods suitable for urban areas are the recharge pits, recharge trenches, abundant tube wells, recharge dug wells, and recharge shafts with or without the tube wells. Then we have the artificial recharge methods suitable for rural areas, which are the gully plug, contour bund, gabion structure, percolation tank, check dam, cement plug, nala bund, recharge shaft, dug well, recharge groundwater dams, subsurface dikes. Artificial recharge practices are the surface practices by constructing ponds and percolation dams, and the subsurface practices content bending, trenching, cement plugging, nala bending, injection well, recharge shaft or trench, dug well, recharge, ditch and contour bunds. In areas with irregular undulating topography, shallow flat bottom and closely spaced ditches, furrows or contour bunds are constructed for recharging the groundwater. The furrow depth is kept according to the topography and also with the aim that maximum wetted surface is available along with maintenance of uniform speed. Ditches should have slope to maintain flow speed and minimum deposition of sediments. Ditches should be shallow, flat bottom and closely spaced to obtain maximum contact area. Counterband is most effective method of conserving soil moisture and is suited in low rainfall areas like Rajasthan. Counterbanding is suitable on lands with the moderate slopes without involving terracing. Spacing between the two counterbands depends upon the slope of the area and permeability. The ability of water to flow through a soil is referred to as the soil's permeability of the soil. Then the percolation tanks or the spreading basin. Percolation tank is an artificially created water body so that the surface runoff is made to percolate and recharge the groundwater. These are the most prevalent structures in India as a major to recharge a groundwater reservoir both in the alluvial as well as the hard rock formation. Percolation tanks are water storage tanks with the highly porous material as the bottom surface material so that the water percolates into the ground very rapidly. The percolation tanks are located on the highly fractured and the weathered rock formations or in boulder formation, which are very ideal places for percolation tanks to avoid erosion of embankment due to ripple action. Stone pitching be provided upstream up to the highest flood level. The recharge area downstream should have sufficient number of wells and cultivable land to benefit from the augmented groundwater. The percolation tanks are designed for storage capacity of the 30 to 60 million liter. Check dams, cement plug and nala bunds. Check dams are constructed across small streams having gentle slope. The water stored in these structures is mostly confined to stream bores and the height is normally less than 2 meter. These are designed based on the stream width and excess water is allowed to flow over the wall. To harness the maximum runoff in the stream, a series of such check dams can be constructed to have recharge on regional scale. Nala bunds are constructed across bigger nalas. The nala bund act like some mini percolation tank. The width of the nala bed should be at least 5 meter and not exceed 15 meter, and depth of bed should not be less than 1 meter. The bottom of the nala bed should be sufficiently permeable. The site selected should have sufficient thickness of the permeable bed or weathered formation of facilitate recharge of stored water within short span of time. The check dams are the most popular and feasible in Bhabar Kandi areas of the Uttar Pradesh, Punjab and Maharashtra. To harness the maximum runoff in the stream, a series of such check dams can be constructed to have recharge on regional scale. We have the gabion structure. This is the kind of check dam being commonly constructed across small streams. The boulders locally available are stored in the steel wire. This is put up across the stream mesh to make it as a small dam by anchoring it to the stream side. The height of the Gavian structure is around 0.5 meter and is normally used in streams with the width of about 10 to 15 meter. The silt content of stream water in due course is deposited in the interstices of the boulders to make it more impermeable and helps in retaining surface water runoff for sufficient time after rains to recharge. The excess water overflows from the structure, storing some water to reserve as source of recharge. The dug well recharge. Dug wells are wide diameter wells used for water supply in the houses as well as in the agricultural fields in alluvial as well as hard rock areas of the India. There are a number of dug wells which have either gone dry or the water levels have declined considerably. These dug wells can be used as structures to recharge. Both existing and abundant dug wells may be utilized as recharge structures after proper cleaning. The groundwater reservoirs, stormwater, tank water, and canal water, etc., can be diverted into these structures to directly recharge the dried aquifer. The recharge water is guided through a pipe to the bottom of well below the water level to avoid scouring of the bottom and entrapment of the air bubbles in the aquifer. The quality of source water, including the silt content, should be such that the quality of groundwater reservoir is not deteriorated. Recharge through dug wells is generally fast. Recharge water should be silt free, and to ensure silt free water, the runoff water should pass either through a desilting chamber or filtered chamber. Periodic chlorination should be done to control bacteriological contamination. Recharge pits and ditches. Recharge pits are constructed for recharging the shallow aquifers, which means sand is generally present from the surface onward. In hard rock areas, the surface soil and weathered formation is suitable for construction of pits and ditches. These are constructed 1 to 2 meter wide and 2 to 3 meter deep and are back filled with boulders, gravels, and the coarse sand. Borehole is constructed inside the recharge pit if impervious layer clay real exists at shallow depth. That is at surface and sand is present below the clay. Ditches or trenches are constructed when the permeable strata is available at shallow depth. Trench may be 0.5 to 1 meter wide and 1 to 1.5 meter deep and 10 to 20 meter long depending upon availability of the water. These are backfilled with filter materials. Pits and trenches are suitable for small houses and the green belts. Recharge shaft. These are the most efficient and the cost effective structures to recharge the aquifer directly. The recharge shafts are also generally round and wide diameter in nature. Recharge shafts are dug manually. Diameter of the shaft should normally be more than 2 meters to accommodate more water and to avoid eddies in the well. The areas where source water contains silt and the shaft should be filled with boulder, good and sand from uh, bottom to have inverted filler. The uppermost sandy layer has to be removed and cleaned periodically. A filter is provided before the source water enters the shaft. If the aquifer is available at a greater depth, that is 20 meter or more, and water levels are deeper than 15, a shallow shaft of 2 to 5 diameter and 3 to 5 meter deep may be constructed depending upon availability of runoff. Inside the shaft, a recharge well of 150 to 300 millimeter diameter is constructed for recharging the available water to the deeper aquifer at the bottom of the shaft. A filter media is provided to avoid choking of the recharge well. These types of recharge structures are the most suitable for group housing societies, large residential and institutional buildings, and office complexes and along roads, etc. Recharge trenches with the tube wells. In areas where sand is present both at the shallow and deep levels for recharging the both shallow as well as deeper aquifers, lateral trenches are 1.5 to 3 meter wide and 10 to 30 meter long, depending upon availability of water with one or more bore wells driven in it may be constructed. The lateral trench is backfilled with boulders, gravels, and the coarse sand. A runoff of the storm drain is diverted to the recharge structure for recharge to groundwater. These structures are best suitable for group housing societies, large residential and institutional areas, office campus, and along the roads. Recharge to injection wells. Injection wells are similar to tube wells but with the purpose of augmenting the groundwater storage of a confined aquifer by pumping in treated surface water under pressure. The injection wells are advantageous when land is scarce. In alluvial region, injection well recharging a single aquifer or multiple aquifers can be constructed. Injection well technique for artificial recharge is comparatively costlier and requires specialized techniques of the tube well construction supported by continuous maintenance to protect the recharge tube well from clogging. Then we have the induced recharge. It is an indirect method of artificial recharge involving pumping from aquifer which is connected with surface water body like river or lake. In this method, the surface water is passed through the sand layer so that the surface water gets clean and can be used for drinking and other uses. The greatest advantages of this method is that under favorable hydrogeological condition, the quality of surface water generally improves due to its path through the aquifer material before it is discharged from the pumping well. The subsurface dikes. Subsurface dike or underground dam is a subsurface barrier across stream which retard the base flow and stores water upstream below ground surface. The site where subsurface dike is proposed should have shallow impervious layer with wide valley and a narrow outlet. After selection site, a trench of 1 to 2 meter wide is dug across the breadth of the stream down to impermeable bed. The trench may be filled with clay or brick concrete wall up to 0.5 meter below ground level. Next, we have the alluvial, the soil layers consisting of or formed by the sediment deposited by the flowing water in the aquifer, water-bearing subsurface strata which stores as well as the releases water. Catchment at the areas contributing to the runoff, then the clogging, the blockage or filter material by fine soil particles and other foreign material resulting in the reduction of recharge. Then the desiltation chamber, a chamber to soil particles and other impurities to settle down in order to ensure clear water free. The percolation tanks are the water storage tanks with porous bottom material so that water percolates into the ground very rapidly. Then we have the permeability. This refers to the ability of the water to flow through a soil. Then the runoff amount of water flowing in a stream as a result of the rainwater harvested from the watershed. Seawater ingress, the entrance of the seawater, subsurface reservoir, groundwater storage, a tube well or the bore well, a hole drilled below the ground for tapping groundwater from aquifer, the water table, water level measured from the ground surface.